All right, the last thing we're covering today is a very specific transformation. It's a translation. You did this a lot in Algebra 1, we just didn't call it this. You also did it in physics with vectors, so we worked with those. But remember, a transformation is a one-to-one relationship where I just move or change a diagram in a graph. Well, a translation is a transformation where all the points of the figures are moved the same distance in the same direction. And we actually use what are called vectors to do that. Now, we also have a term, and I want to make sure you memorize this. It's called an isometry. A translation is an isometry. An isometry is when an isometry is, let me just do this, is a transformation that preserves size and shape, which means reflections, rotations, and translations are all isometries. Dilations would not do that. So that's why we call a translation isometry, because it keeps the size and shape. Now, first thing we're going to do, can I decide if these two figures are translations from what we learned earlier? Remember, a translation is also known as a glide. All right? Did I glide these two? No. You could see that's a reflection. But here, you can see that I translate this. You can see this moves the same direction and distance. So this one is yes. Images move same direction and distance. Now, how do I know if it didn't go the other way? It could. I'm just showing you how it works. You can see how every one of these are parallel, and if you'd measure it, they're all the same length. Let me do it real quick here for you. This would be about 2 centimeters, 2 centimeters, 2 centimeters, 2 centimeters. So it works out pretty well. But here's the cool thing. To do that, we have to use what's called a vector, okay? A vector is just an arrow that tells you how far I'm going. The length of the vector tells you how far you're moving, and the way that the vector is pointing, and by the way, technical term in geometry we'd call array, okay, tells you which direction. So how far and the direction. So it's not too hard to show how it translates. And you can do this very easily with just a folded piece of paper. And I'm going to grab a piece of paper here. Fold a piece of scratch paper in half. And some of you are good eyeballers, so you could probably eyeball this. I'm not, okay? To draw a translation using a translation vector, and the little symbol for vector, if you notice, is like this little half ray right there. Oops, I need to move it up so you can see it. And what I do is I go, okay, I'm going to go upside down, and you can eyeball this pretty well. You can draw lines going through each vertice that are parallel to the vector. So I'm going to keep it going parallel to the vector. Here's another one. Parallel to the vector. Those are all parallel to the vector. But now the vector also tells us direction. So I go here and distance. So I go and I literally measure like, you know, Euclid did. Keep it very simple and mark it. That's how far from here to the end of my paper is going to be the direction I'm going to go. So I go to each vertex. Here would be one of them. Here would be I move this vertex to here. And I go from this vertex, get its length. I get the top one here. And I mark those 4 vertices, and then I just use a straight edge, or you can eyeball these, and you can draw it in. There you get your new image. Notice I went this way in the direction that our vector gave us. Went this way. Same distance, same direction. It literally should look like I slid it over. Now I'm going to do the same type of idea for B. Now here, I have to go through each vertex and make sure that I go through so it's parallel to the vector. So this time I'd make them long, and I go upside down when I do this just so I can see my parallel. Now notice I'm just asking you to eyeball this. I don't expect perfection, but you should be able to get a pretty rough idea how these are drawn. right, so those are all my parallel lines. The same, all right, the same direction basically is what I'm going. Now I have to do distance. So I measure this one just the magic way that I did before. And if you're watching this video, you might want to stop and get caught up with me. You match the points. I go to each vertex and I mark its image. Go here, show you how far it moved. So when you do that, if you connect them, you should be able to see that. All right, so let's go ahead and flip it over and apply this just a little bit.